The vast majority of Lecture 5b for Differential Equations and Linear Algebra is about linear algebra, but I thought it would be good to spend a minute or so just cleaning up some things at the end of Lecture 5a that I wish I had emphasized, but I didn't. We were looking at trying to approximate the true solution of a certain differential equation with Euler's method. We got data. I mentioned how the black dots are the data points essentially. The coordinates of these points are t0 and v0. T1 and V1, T2 and V2, where V was a function of time. The velocity is a function of time for an object falling under the influence of gravity with air resistance. What I wanted to emphasize here is that Euler's method, again, is created by essentially a linear approximation. At this point, the tangent line to the solution curve has a slope equal to the blue line slope in the slope field. And by making a straight line right there to connect to this point, we are essentially following that tangent line forward in time by half a second in this case. We get to this new point, there's a new slope for the true solution that happens to go through that point, given by the slope of the little blue line in the slope field at that point. This line segment essentially follows that tangent line forward in time, also by 0.5 seconds. So that, again, emphasizes the meaning of Euler's method that you should understand as well. All right, now on to the linear algebra. The linear algebra content for this lecture is applications of dot products and vector normalization. That would include the main application being the projection of one vector along another. I haven't said what that means yet. And we're also going to look at a system of 2x2 equations, two equations and two unknowns, a linear system. We'll look at solving that by elimination and also generalizing what happens. The reading for this is at my blog, infinityisreallybig.com. The book that I'm writing there about linear algebra is called Visual Linear Algebra Online. All right, on to the content. It's a physics application, just like in Lecture 5a. We were doing free fall. Now we do another physics application. We're trying to find something called the work done by a force. It's going to be a force going against gravity to move a certain mass up a certain inclined plane shown below. Here's the below. Assume the magnitude of the force is 8 newtons constant force, and that the displacement vector is the red vector here that you see labeled D. We've talked about vectors, what they are, how they're symbolized, and how they're drawn, and their properties in recent lectures. Now we're trying to use them. This brown object here is like a block of wood. It's mass m. We're trying to push it up this inclined plane against gravity, and we're wondering how much work needs to be done. What is work? It's essentially energy, and the units are in fact units of energy, which is joules. I'm not going to get into the details of why the work done is the way that it is. I'm just going to tell you what the physics teachers will tell you. Essentially, we want to multiply the magnitude of the force in the direction of motion, which is this direction, times the size, the magnitude of that actual displacement, the distance traveled, if you will. Okay? But there's a catch here in that the force that we are pushing this block of wood with is not parallel to the inclined plane. It's a horizontal pushing that is moving it up. We're not going to worry about the nature of the force of gravity. We're also not going to worry about friction and normal forces, that kind of thing. That makes it too complicated. We can keep it simpler just by focusing on what you see in the diagram here. What is D as a vector? Well, I picked a particular D. This is not something to derive. This is just something I picked. The components of D are 10 and 10 times over the square root of 3. If you were using standard physics notation here, you would write this in what's called I hat, J hat notation. You would write 10 I hat, the 10 matching the first component up here, plus 10 over root 3 J hat, the 10 over root 3 matching the second component right there, which is approximately 5.7735. What are I hat and J hat? They are called the standard basis vectors that are also unit vectors. They have a length of 1. I hat points straight to the right, J hat points straight up. The point in writing the vector this way is that you can imagine it as scaling I hat up by a factor of 10, making it 10 times longer in the horizontal direction, scaling j hat up by a factor of 10 over root 3, which is about 5.7735, making it longer in the vertical direction, and adding those two vectors together to get this d vector. The sum of these two things, this vector sum, is this red vector that you see here. We will more typically write it as column vectors here for the components, because that'll be more useful for what we do for our purposes, which include multiplying matrices times vectors relatively soon here, maybe even in the next lecture or two. I'm not positive that we'll do that, but relatively soon. The answer, like I just told you, how to find the work done, I'm not telling you why this is what you do, is the product of the length of what's called the projection of f along the direction of d, I haven't said what that is, times the length of the vector d. That's the answer for the work done. Okay? So find those two things and multiply them to get the answer. What is the projection of f along d? I like to think of it as the shadow of f along d. If you imagine a light source coming in perpendicular to d, in this direction here, then this arrow is going to be the shadow of f along this red vector. Now, I'm not sure that picture is perfect. This is supposed to be a right angle here. I'm not sure if that looks like a right angle or not. I can't quite tell just looking at it. It's close. That would be the shadow. This blue arrow right here would be the shadow of f along this vector d. That's called its projection, and I use this notation for the projection. Projection of f along d, along the direction of d. If f were longer, its projection would be longer. If f were shorter, its projection would be shorter. What if f pointed in, say, that direction, down that way? Then its projection along d would go that way, actually. It'd be along the same line, but go the opposite direction. It would not point in the same direction as d. Here, this projection is a positive scalar multiple of d. If a projection were over here, the projection would be a negative scalar multiple of d. In components, f is 8, 0. Okay? F points horizontal, so its first component, and to the right, so its first component is positive, and its second component is 0 because it's horizontal. No vertical component to f here. Don't be bothered by the fact that the units for these things would be different. D would be in meters if we took its magnitude, and if we took the magnitude of f, it would be in newtons. Don't worry about that, okay? The unit's going to work out fine in the end. We just get joules in the end. So, how do we find that projection vector, or at least to solve the problem, we only need to find its length. It's going to be an important application of dot products in vector normalization. Well, we can use trigonometry. There's a right triangle, right? Here we go. Right triangle right there. This triangle right here with the right angle right there. So we should be able to use trigonometry. And we know the length of f is 8. And we're given that this is a 30-degree angle. That's given to you. I'm telling you that. Cosine of 30 degrees, so cot-TOA, cosine is adjacent over hypotenuse. The length of the projection divided by 8. We could write that this way. We could solve for the length of the projection vector. The length of this side, notice the double absent value signs, that means length or magnitude of the vector. That's the notation that we're going to use in this course. Is the length of the hypotenuse, which is 8, times the cosine of the angle. This angle is what theta is right there. Okay. The 30 degrees I'm just giving to you. I'm telling you it's 30 degrees. This is equivalent to saying cosine of theta is this quantity divided by this quantity right there. Adjacent divided by hypotenuse. Plug in the numbers. Length of f is 8. Angle is 30 degrees. Cosine of 30 degrees is square root of 3 over 2. That simplifies to 4 times square root of 3, which is about 6.9282. So there's the length of the projection vector. What about the length of d? We can use the Pythagorean formula on the bigger triangle, right? The bigger right triangle, there's another right angle right there. The length of the red vector is the square root of the squares of the lengths of the two sides, this side right here and this side right there. But those numbers come from the components of D itself, 10 and 10 over root 3. 10 squared is 100, 10 over root 3 squared is 100 over 3. Get a common denominator of 3. You're going to get 400 over 3 in the square root. Square root of 400 is 20. We can just leave the square root on the bottom. And that's about 11.547. By the way, a little aside here, it's fine to leave the answer like this. You do not have to rationalize the denominator. I don't care. I mean, yes, that's equivalent. It's equivalent to 20 root 3 over 3, where I get from here to here by multiplying the top and the bottom by root 3. You don't have to do that. It's not required. It's not a mathematical sin to have radicals in denominators. It's okay. It's not like dividing by 0. So why did your teacher tell you to do that? 2 reasons. It is a useful skill sometimes. Rationalizing the denominator is just a useful skill to solve problems in certain situations. And it also makes things easier to grade because it gives you the same final answer. The same form for the final answer. These are both equal to each other, just different forms of the same number. Therefore, the work done is the product of these two things. 4 root 3 times 20 over root 3. The root 3's will cancel and leave you with 80. It's about 6.9282 times 11.547. If you multiply those numbers, you won't get exactly 80 because those are just approximations. But the true answer is 80, and the units are joules. But this last expression, here's something very important. This last expression, the 80, and in fact this formula here, is the same as the geometric formula for the dot product of f and d. Sometimes I'm using the little half arrows above my vectors, sometimes I'm bold facing my vectors. Don't let it bother you. Right? Talked about that in lecture 4b, the dot product of two vectors. V dot W, say, you can find by adding the products of their components, but you also can find by taking the length of V times the length of W times the cosine of the angle between them. That's the geometric definition. You have to show they give you the same answer. That requires the law of cosines. That's what I've got here. The length of F, the length of D, the cosine of the angle between them. Theta is the angle between them. And if you use the components, you do see you get 80. Okay, gives you the same answer. And that, then, if you know the components, would be a quicker way to find the answer. Hey, that's good. A quicker way to find the answer for the work done. It's no accident that that happens. That's going to happen in general. It's also useful to be able to find the components of the projection vector itself. We didn't do that. We just found its length. We found the length of that shorter blue vector along the inclined plane. But it's also be able to be useful to find its components. That's a useful thing too, it turns out. Here's a two-step process to find it, and here's an application of normalization. First, normalize. Find a unit vector in the same direction as the vector d. D was the red vector, the displacement vector along the inclined plane. In lecture 4b, we called that process normalization, where you find a vector of unit length, length 1, in the same direction. And you do that by dividing the vector by its length. Or what's better to call that is multiplying by the reciprocal of the length, like this. It's called the vector u for unit vector. 1 over the length of d times d. This scalar times that vector gives you a vector that has unit length. The length of d is 20 over root 3. The components of d are 10 and 10 over root 3. Multiplying by 1 over 20 over root 3 is the same as multiplying by root 3 over 20. This thing is the same as root 3 over 20. Multiply that by 10. The 10 and 20 cancel to give you 1/2 times root 3. Root 3 over 2. Multiply this by the second component, the root 3's cancel. You're left with 10 over 20, which is 1/2. This is a unit vector. It's got unit length, which you should be able to imagine checking with the Pythagorean Theorem. And get the square root of 3 over 2 squared, for example, would be 3/4, and 1/2 squared would be 1/4. 3/4 plus 1/4 is 1. This is a unit vector. Square root of 1 is 1. It's approximately that. Then what? What's our goal again? Our goal is to find this projection vector, which was, again, the blue vector along the inclined plane that was shorter than the red vector. U has the same direction as D. It's still pointing in the same direction, but it's got unit length, length 1. If I rescale it to have length equal to the length of the projection vector, which we already found, that would do it. Multiply this vector by the desired length. The projection vector, this is a vector that I just underlined, is this scalar times this unit vector. The unit vector has length 1. I'm rescaling it by this number, the length of the projection vector, which I know is this product here, the length of f times the cosine of theta. Right, that came from the trigonometry. And that was the thing that was 4 times root 3. 4 times root 3. U has these components, multiply 4 root 3 times root 3 over 2. The square root of 3's squared gives you 3. 4 divided by 2 is 2. 2 times 3 is 6. 4 root 3 times 1/2. The 4 and the 2 cancel will leave you with 2 root 3. It's approximately that. That is the projection vector. Not telling you what it's useful for, but it turns out it does have its uses. You can do some slick algebra to do all this in one formula. This is pretty tricky to derive this, but you can understand it. It's just tricky to derive. So far, this part is the same as up here. This part is the length of the projection vector. The unit vector here is this. Now I'm writing it as d divided by its length, but again, it really is 1 over the length times d, the reciprocal of the length times the vector. And a little algebraic trickery is that I can multiply by a disguised form of 1, which essentially is the length of d divided by the length of d. I put a square there, but then I need an extra factor of the length of d there, the magnitude of d. And then finally, that can be simplified. This part right here is the same as f dot d, right? That's this. And then remember, this is something I mentioned in the last lecture 4b. The length of d squared is actually d dotted with itself. I did mention that in lecture 4b. To give you this final expression here, you see, that's a one-step formula, so to speak, to find the projection vector. Of course, you got to do more than one step when you actually use the formula. It's one formula for the projection vector. I would encourage you to check it and see that you get the same answer. See that you still get, where is it? Right here. You should pause the video to check that. Okay, on to our second main topic of lecture 5b, systems of linear equations. So in my book, Visual Linear Algebra Online, and my blog, infinityisreallybig.com, section 1.2 is about vectors, which we just did. Section 1.3 is about systems of linear equations. So we're doing parts of both sections here. Solve this system of linear equations right here. Maybe you want to go ahead and pause the video here as well and go ahead and solve this. It is a system of linear equations. These equations are linear. They only involve x and y to first powers, no squares, no square roots, no e to the x's or cosines of y's. And it is a system. They go together. We're trying to solve for values of x and y that make both equations true simultaneously at the same time. Probably the simplest way to solve it is with what's called substitution. You could solve the second equation, for example, for x in terms of y, you'd get x is 10 minus 2y. And then you could substitute that into the first equation in place of x. To get 5 times, in parentheses, 10 minus 2y, and then you'd have a minus 3y equals 11. You'd simplify, solve for y. Then you'd go back to the other equation, or this equation, and plug in y to find x. I'm going to show you the elimination method, which is going to be more steps, but it's going to generalize better to higher dimensional problems. So you want to learn elimination. We're also going to use matrices ultimately when we do this as well. First step is an unnecessary step, but I'm going to do it anyway because it's an allowed row operation. I can switch the two equations around. So the original first equation here becomes the second equation here. The original second equation here becomes the first. I flip the two rows, the two equations. That is allowed, right? These equations, these systems are equivalent to each other. Now, how do you do the elimination? You want to imagine multiplying the first equation by something such that when you add it to the second, either the x or the y cancels. The typical thing to do in this kind of algorithm is to try to cancel the x's first. So I'm going to multiply the first equation by -5 so that I get a -5x there, so that when I add that to +5x, I get a 0. The x goes away. I'm going to also write the new first equation here initially to emphasize what's going on. You don't have to show this step. You could just skip from this step to the next step that's going to come. But just for the sake of clarity, I'm going to include it here. So I'm multiplying the first equation, everything, by -5. -5 times x is -5x. -5 times 2y is -10y. -5 times 10 is -50. Keep the second equation as is. Now I'm going to add these two equations. The -5x plus 5x will cancel to give 0. I'll get -10y plus -3y is -13y. Careful, you're not subtracting the equations, you're adding them. To get -13y, -50 plus 11 is -39. I'll get -13y equals -39. Y would be 3. I'm going to show that here. I'm going to go back to the original first equation that I had right there. Okay, so that's part of why I'm saying you could really skip this intermediate step, go from here to here. Because I am purposely making the original equation, the first equation, the same as it was there. It's not that I can't write it that way, it's just simpler to write it this way again. These are all equivalent systems of equations. Whatever is a solution to one of them is a solution to the others. The logic here in doing what I'm doing is that I'm really assuming I've got a solution here and I'm trying to figure out if I have a solution, what is it? That's really the logic. It's really not proving that it's a solution in the end, that comes from checking. What I'm going to do now, I'm going to solve for y. I'm going to divide the second equation by -13 on both sides. -13 divided by -13 is +1. I get just a y on the left. -39 divided by -13 is +3. Gives me this equation. Y must be 3. I could substitute the 3 in here right away. Get 2 times 3 is 6. 10 minus 6 is 4. X is going to be 4, but let's think about it a bit more systematically. I want to now do a row operation where I eliminate the 2y in the first equation. I want to multiply the second equation by -2 and add to the first equation. -2y plus 2y will be 0y, just 0. -2 times 3 is -6 plus 10 is +4. But I'm going to show the -2y equals -6 here. This is a step that's optional. Now add and put the answer in the top. -2y plus 2y is 0. By the way, 0x plus x is x, so the x doesn't get affected. -6 plus 10 is 4. The only possible solution is the ordered pair 4, 3. In fact, it is a solution. You can check, so it is, in fact, a unique solution. How do you check it? You just go back to the original system and plug the numbers in. And see that left-hand side equals right-hand side for both equations. 5 times, looking at the upper left there with these numbers, x is 4, minus 3 times y is 3, does give you 20 minus 9, which is 11. Left-hand side equals right-hand side when I plug the numbers into this first equation in the first system. What about the second equation? X, which is 4, plus 2y, which is 2 times 3, is 4 plus 6 is 10. Yes, that works too. This is the left-hand side, and this is the right-hand side. I get the same thing when I plug these numbers into the second equation. So the checking is really more than just making sure you don't make a mistake. Hope that's not cut off there. Just thought about that. Could have happened in the first lecture too, 5A. The checking is more than just making sure you don't make a mistake, though that is a good reason to do it. Logically speaking, that is the verification that it really is a solution. This logic is telling us if I have a solution, if I assume these equations are both true, then x must be 4 and y must be 3 is the only possible solution. It's not saying it is a solution. The checking is the proving that it is a solution. So in fact, it must be unique. It is a solution, and it's the only one. Geometrically, we can graph the original equations in, say, a rectangular coordinate plane, Cartesian coordinate plane, and see where the two lines intersect. Maybe you want to pause the video and do that. I'm also, just for fun, going to plot in polar coordinates. Why would I do that? That is just for fun. Where I'm going to treat the r as the x and the theta as the y. Could have actually switched it around and treated the r as the y and the theta as the x, and in some ways that actually makes more sense. But don't worry about it. Here's the picture in rectangular coordinates, the standard kind of thing. Graph paper. Coordinate system imposed on a plane. X-axis, y-axis. I've made the units on both axes the same. 5x minus 3y is the red graph. If I solve for y as a function of x, it would have a slope of 5/3, which looks about right, and a y-intercept of negative 11/3, negative 3.6 repeating, which looks about right as well. And the blue graph is the other equation, x plus 2y equals 10. Y as a function of x, y would be negative 1/2 x plus 5, yes. Slope of negative 1/2, y-intercept of 5. For fun, I can plot it in polar coordinates. Though if you do plot it in polar coordinates, funny things can happen. You can actually get more than one intersection point because the angle's not unique and because r can also be negative. But if you plot it where theta goes between, say, 0 and, I pick 3 pi over 2, which is about, what, 4 something, I think. You get this picture. And they intersect at this point, whose polar coordinates are r equals 4 and theta equals 3. R equals 4 means you're 4 units of distance from the origin. You're along a circle of radius for this circle here. So r is 4. And theta is 3. You know, pi radians is 3.14 radians approximately is 180 degrees. We're almost at an angle of 180 degrees there. This ray, that angle right there is 3 radians. 3 radians. How are these graphs made? Well, I made them on the computer, but if you needed to make them by hand, you want to take these same equations and solve for r as a function of theta. That's not equivalent to solving for y as a function of x. It's really equivalent to solving for x as a function of y, because r is like the x and theta is like the y. So in that sense, it's a bit confusing. Then you'd let theta vary between 0 and 3 pi over 2 here, and you'd, for each value of theta, for each angle, you'd use the equation to figure out how far from the origin it should be. So for example, when theta is 0, 10 minus 0 is 10. You are 10 units from the origin. When theta is, for example, 1 radian, 10 minus 2 is 8 distance units from the origin. So that would actually be, you can even see where that is here. Going to be 8 units away from the origin. Where is it? Right here. That angle, which is a little less than 60 degrees, oops, is theta equals 1 radian. I think it's like 57 degrees or something. Right up there. That angle is 1 radian. And you can do something similar with the red graph. When theta is 0 here, you get 11/5. This point here is 2.2 units from the origin. And it gets further from the origin as theta increases because this is an increasing function of theta. The blue one gets closer to the origin as theta increases. So R decreases up there. Now R can become negative. So again, funny things happen when you let theta go too far. And it actually can intersect more than once. But this is emphasizing that it could be visualized this way. Why? Just for fun. Polar coordinates is not just for fun, though. It's a useful thing, and we will see some uses later on, even though it's not really linear algebra. Linear systems with 0 or infinitely many solutions can also occur. That last system we looked at had a unique solution, but we can also look at systems with 0 or infinitely many solutions. Let's consider a system like this. 2x minus y equals u, and negative 4x plus 2y equals v, where u and v are unspecified numbers. Are they constants? You could pretend they're constants. There are going to be situations where we pretend they're variables. Pretend they're constants for the moment. Notice that the left-hand sides here are constant multiples of each other. If you multiply the top equation by positive 2, and add it to the first equation, both the x and the y terms will cancel. In fact, let's do that here. Multiply the first equation by positive 2. 2x times 2 is 4x. Negative y times 2 is negative 2y. U times 2 is 2u. Now add these equations. You get 0 on the left-hand side of the second equation when you do the elimination. And what do you get on the right-hand side? Well, you get 2u plus v, which is what you see there. What does this mean? Well, remember the logic. The logic is when we start here, with our system, we're assuming we got a solution when we try to solve. And we're trying to figure out if there is a solution, what is it? Assume there are numbers x and y that make both equations true simultaneously. What happens? We get to a statement here that could be true and it could be false, depending on what u and v are. Again, pretend u and v are something specific. I mean, you could pick specific numbers. 2u plus v might be 0, it might not be. That equation might be true, it might not be. What if it's not true? What if 2u plus v ends up being 17? If that's true, based on the given u and v, we would have gotten the conclusion that 0 equals 17, which is obviously false. We would have gotten a contradiction, a logical contradiction to the assumption that there are solutions. And what that would mean is there really are no solutions in that case. On the other hand, 2u plus v could equal 0. If v were 2 and u was negative 1, that would be 0. U was negative 1 and v is 2. You would have a solution. 0, this equation would say 0 equals 0 in that case. And the solution would be completely specified just by the first equation. And that would represent infinitely many answers, because that would represent a line. When u is fixed, like at negative 1, that would represent a line of points in the plane. And all those points would solve the system in that case. Here's what I just said. What does this mean? It means the only way there are solutions is if 2u plus v equals 0. The only way there are solutions is if 2u plus v equals 0. In that case, there are infinitely many solutions all on the line. Otherwise, we get a logical contradiction, and there are no solutions. 0 solutions. I'm saying 0 or infinitely many. I'm talking about the number of solutions. I'm not saying 0 is a solution. In that case, we'd say the system is inconsistent. For example, if u is 5 and v is negative 10, then 2u plus v will be 0. And in that case, we can represent the solution set based on this first equation in this form. I'm using what's called set builder notation here. I'm saying the solution set, the curly braces here and here represent sets that are collections of things, in this case collections of points, ordered pairs, which I could visualize either in a rectangular coordinate system, which I typically will do, or polar coordinates or some other coordinate system, like a skew coordinate system. This vertical line here means such that, or with the property that 2x minus y equals 5. Why I pick 5? Because that's what I'm letting u be here. Did I have to pick 5? No, I could have picked something different. I could have let u be 4 and v be negative 8. Or u be negative 4 and v be positive 8. U is 5 here, and this equation can be solved for y as a function of x. That line with a slope of 2 and a y-intercept of negative 5, when plotted in a rectangular coordinate system, is the solution set visualized. Technically speaking, you don't have to visualize it. You can just say it's the set of ordered pairs as the solution set. But it's useful to visualize it. And we can do so. And I will do so here in a second. But before we do that, and this is, by the way, this is the last slide, we can also visualize the solution set vectorially. What do I mean by that? You remember that when I first started talking about vectors, I mentioned there's a natural association with points in the plane and arrows. I think it was lecture 3b. For any point in the plane, there's a corresponding position vector. You draw your rectangular coordinate system, you've got your origin, draw an arrow from the origin to that given point. That's its position vector. Likewise, given any arrow, I can translate it so its tail, its initial point is at the origin. Whatever point the head is at is the corresponding point that it goes with. The coordinates of the point match the components of the vector as well. So I don't have to think of this as a set of points that are solutions. I can think of it as a set of vectors, and I'm going to write them as column vectors. The solution set could be thought of as a set of ordered pairs, which could be imagined as points, or could be thought of as a set of column vectors, which could be imagined as arrows. And these are equivalent. Notice I've replaced the y here with 2x minus 5, because that matches this. That's where that comes from. Where such that x ranges over the entire real number system. That funny thing there, that funny r, represents the real number system. The set of all reals. I'll just write reals, though it's really a set. This funny thing here means is an element of, or is in for short, though saying is an element of is better. X is in R, X is an element of R, meaning X is a real number. All vectors of this form, which can be decomposed component-wise into this form. I'm about to say is really useful here, hang on with me. When we do this, we also think of X as what's called a free variable. X can be anything, any real number, and Y would not be a free variable. I'm going to go ahead and give these vectors name. This one I'm going to call V, those match. And this one right here I'm going to call W, these match. And I'm about to visualize the solution set, not just as a line, but as a collection of vectors, as position vectors that match the points on the line, and that change as x changes. I'm going to show you an animation. And that can be thought of vectorially in terms of scalar multiplication and vector addition. Here's what I mean. Look at this picture. The green line is the solution set as a set of points. That's the line y equals 2x minus 5. Slope of 2, y-intercept of negative 5. The pink vectors, as x varies, are position vectors for points on that green line. The pink vectors are solutions to the system when thought of as vectors. And those pink arrows, those pink vectors, can be thought of as the blue vector, the fixed v vector, plus x times w. V plus xw when you think about adding vectors head to tail. The tail of the red vector is at the head of the blue vector. And the sum for any given fixed x is the corresponding pink vector. And x is free to vary. And as x varies over all real numbers, you get in the entire green line, so to speak, as matching the position vectors that vary, the pink ones that vary. When x is positive, x times w is in the same direction as w. Look at the components of w. They're 1, 2. W points to the northeast. Yeah. And when x is negative, it points in the opposite direction. So it corresponds to scalar multiplication as well. V has component 0, negative 5. It points straight down. Okay? I believe that's the last slide. Yes, it is. Thanks for watching. I hope you enjoyed it.